Hello everyone, welcome to this course on discrete mathematics, and in this series in the last two sections we have been talking about countings, permutations and combinations, and today we will talk about Pascal's triangle. Basically the idea of Pascal's triangle has to do with this combinations and principles that we have just talked about in the last lecture. Let's dive in. Before I go in, I want to give you some background of this Pascal's triangles. So there is this polynomial expansions that you might have studied this. Say for example the x plus y the whole cube can be written as x cube plus 3x square y plus 3xy square plus y cube, and this is in fact is the combination of x plus y times x plus y times x plus y. And again, if you take just x, you have x times x times x is x cube. Then if you take again x times x plus x times y is x square y. Yes, the thing goes on. As you can see that this is a simple algebraic formula, but in fact it is just the combination of various elements related to one another. Yes, that's why we still talk about the permutations and combination and expansion of it. So let's move ahead with this other combinations. Here again you have x plus y the whole power 5. So we can obtain x power 5 term when we multiply x plus y each time. You get x square, x cube, x power 4, x power 5. Yes, that is C of 5 comma 5. So you can also choose y 0 times, that is C of 5 comma 0, that is 1. Or you can choose for x power 4 times y. You have 4 times you are choosing for x plus y. In x plus y you are going for 4 times, you are going to multiply it and you have to select x there, x power 4. The other time you are going to select y. So y is coming once there. That's the choice of, just you have the 5 choices, you choose x power x 4 times and you have y there 1 time. Yeah. So there is different combinations you are coming up with this polynomial expansions. So especially for this x cube and y square, again you have C of 5 comma 3 and C of 5 comma 2, 10 that is. Yes, we have just seen this example here. So different way to express it. So it's just like saying, when I say 5 and 5 here, it's like 5 choose 5. 5 choose 4, 5 choose 3, 5 choose 1, 5 choose 1, 5 choose 2, 5 choose 1, 5 choose 0. So that's the notation that we use to express it. Generally speaking, we can write it as of this form: n choose n choose n minus 1 and so on. This is the general form of the polynomial expansions with respect to binomial theorem. Let's see some examples with x power 12 and y power 13 in x plus y power 25. We started with cube, we went to power 5, and now right now we are in power 25. In power 25 there is a coefficient x power 12 and y power 13. That's what we talk about. So that is 25 13, that is 25 12, that's like 25 by 13, 25 factorial by 13 factorial times 12 factorial. Again, what is the coefficient? Again, for x power 12 and y power 13 in 2x minus 3y power 25. We can just rephrase it just to simplify it, and after simplification you can just use the coefficient to help out in solving this problem here again. So it's similar to the previous one that we have. Again, now you have to choose the coefficient x power 5 and y power 8 in x plus y the whole power 13. That's quite straightforward answer that we have. Yes, now we will talk about the Pascal's triangle. The basic idea of Pascal's triangle is a kind of a geometric version of Pascal's formula, I could say, and it's simply called an arithmetic triangle. You could call it as an arithmetic triangle because it used centuries before. It's kind of an arithmetic triangle. As you can see here, this has been used for centuries. Even the Chinese and Persian mathematicians used similar structures to represent various forms of arithmetic. But Pascal discovered it. He discovered it quite independently from that of Chinese and Persians, and of course he published this work as one of his treatises. So some of the features of this Pascal triangle is quite obvious when you look at this triangle. As you can see here, we have this combinations of 0 and 0, that's n equals 0, and then as you progress, since we talk about this different versions of it, now we can go ahead and see how they are related as for this Pascal's triangle is concerned. And Pascal's triangle, again, the values of Pascal triangles are, it's the values of n, choose or. That's the basic idea and basic definition. So each entry in the triangle is the value of n, choose or, and we have the Pascal's formula translated into the fact of entries. So these entries are actual Pascal's formula that has been translated to define these rows and columns of this elements. And as you can see, the sum of entry in row, say row n, and column, we are adding to form this arithmetic relationship, and there is some interior positions equals to the sum of two entries directly above it, right? Say for example this one, when you choose this, this interior position equals the sum of the two entries, that is 15 and 16. That's a simple reference that we are taking for us to get hold of the idea of this Pascal's triangle. And we can use this Pascal triangle to compute the values of certain numbers and certain combinations that we talk about. Yes, that's what we see here, that is of the form n, choose or. Suppose if you want to compute any particular values, say for example 6 choose 2 and 6 choose 3, you can think about these values. Say for example we are talking about 6 choose 2 and 6 choose 3. What are we looking at? We are looking at these two values, and these two values eventually can reveal us the third value, that is 7 choose 3. Well, let's move on and see how and how well they are related. And by the way, if you could simply look in this form, I talked about 6 choose 2, and generally speaking 6 choose 2 would be of the form 5 choose 1 and plus 5 choose 2, right? If you think how this has come about, right? In speaking of that, you can again go and tell it is 5 plus 10, which is 15, and again 6 choose 3 can have a similar form of 5 choose 2 and 5 choose 3. So that is of the form 10 plus 10. That takes you to 20. Let's talk about this Pascal's identity, as we have just seen earlier here. 7 choose 5 is 6, choose 4 plus 6 choose 5, that is 21, 15 plus 16. And with these identities we can actually perform various operations. In fact, there are different ways to prove it, and we will briefly see what is that proof. But I am not going to let you committed in proving this information, but these proofs are quite useful for you to understand. But the basic idea, the basic concept, once you grab these concepts, it's easy for you to observe and contemplate on what other identities can be developed from this proof. So starting about this algebraic proof, we have this form n plus 1 choose k, and that is revealing as this factor, and with this factor we can substitute these values. Say for example, instead of 1 plus n plus 1 the whole factorial, we say n plus 1 times n factorial. Likewise, you are replacing, as you can see here, we have just replaced that with this. Likewise, once you replace it, substitute these values, and after substitutions of these informations, in fact you can also simplify it, and once you manipulate to simplify it, you get reveal that the overall information in fact takes us to n plus 1 equals n plus 1, that is right hand side is equal to the left hand side. We just proved it, a simple identity of combinatorial proof. We have just seen the algebraic proof. Now we are going to look at the combinatorial proof, in which we are using the C NR methods. So we have this set, we are considering the set, and with n plus 1 elements, and you are going to talk about this information with respect to set and subset. So we want to choose a subset of k elements there, and there we want to count the number of subset of k elements via two methods. Like when we choose the first method to be C n plus 1 k, ways to choose the subset, and method 2 is to let A be an element of set T. In that respect, that would be a subset. So A is such as a subset, and A is not a subset. Again you have two different cases there, A with subset and without subset. So we can go ahead and see how C of n k minus 1 plus C of n comma k, ways to choose the subset of k elements. So this is basically a identity proof of combinatorial proof that we have here. Coming back to this Pascal's triangle, at this point you are clear about what a Pascal's triangle is and how it is applied to the permutation and combination methods that we are discussing, and basic identity of its proof has been also revealed. And again, there is another observation that you can think about. As you can see here, there are different layers of this Pascal triangle starting from 0 onwards, and when you sum up all these values, it brings out another relationship. Yes, can you think of this relationship? 1, 2, 4, 8, 16, 32. Well, that is 2 power n, that's true, right? So that's an interesting observation, and from where we can also go ahead and look at this algebraic proof. So let n be the non-negative integer, then summation k equals 0 to n, where n choose k equals 2 power n. We have just seen that here, 2 power n there. So if you like to look at this definition by means of algebraic proof, 2 power n equals 1 plus 1 power n, and that again is similar to x plus y power n. Again you can represent that by means of summation j equals 0 till n, n choose j times x power n minus j times y power j. So in terms of x and y, right now we can again have this combination of the form n choose k 1 power k and 1 power n minus k. Again, coming back to this form, you have summation k equals 0 to n choose k there. So that's an interesting observation. Again, we can go for, we have seen the algebraic, and now we can talk about this combinatorial proof. And set of n elements, we have 2 power n subset. So that's by means of power set form, and each subset has either 0 or 1 or 2 or any element n. So with this informations, there are n choose 0 subset with 0 elements, and then you have 1 element, and then you have 2 elements, till you have n elements, because all these things, either 0 element, 1 element, 2 element, all these things belong to a subset. These are all subset in fact. So total number of subsets that we have starting from 0 element on is summation k equals 0 to n choose k. That's the same thing that we are interested in. Well, coming back again to the Pascal's triangle. In fact, Pascal's triangle, the theory of this has been published in 1650s. That's been a long time. Though it has been published quite long time, still we are getting some benefit out of it, and see how they are related to one another. As we can see, this combinations here, as the theme moves on, you had 1 1 2 1 3 3 1 1 4 4 6 4 1. Yes, can you see a pattern developing there? Right. So this is a simple form in which we can come up with a proof for our practice. So n be a positive integer, and with that we have summation k equals 0 to n minus 1 power k n choose k equals 0. So with this algebraic proof, we can say that 0 equals 0 power n, so minus 1 plus 1 power n, again x and y formula that we have used before. So with this reference, we can move ahead and see how this has been dealt with, and this in fact implies that n of n choose 0 plus n choose 2 plus n choose 4 so on equals n choose 1 plus n choose 3 and n choose 5. In fact, these things are all subsets, if you can look at that point of view, and when you add these both parts, then you would be coming to this conclusion. Then again, n is the non-negative integer, with then you have summation k equals 0 to n 2 power k n choose k equals 3 power n. Again, you have to go for this 3 power n equals 1 plus 2 power n, and that again you are going backwards to find the solution. 1 times 1 power k minus 1 power n minus k times 2 power k, and again you are trying to utilize this fact and trying to find the solution for that ideas. So now let's look at this simple Vandermonde identity, where we can say that let m and n and r be the non-negative integers, with r not exceeding either m or n. Then you have this form m plus n equals, or m plus n choose r equals summation k equals 0 to r m choose r minus k n choose k. So with this identity, you can think about some places where it can be used. Assume a congressional committee must consist of r people, and there are n Democrats and m Republicans. We talk about an example here. So how many ways are there to pick the committee? So that's where this whole combination of this identity comes in. How many different ways? So from the previous thing, we just saw that we have this form which we can use to identify the solutions. So consider two sets, one with m items and one with n items. So we talk about the two different groups here. So let's say this first part, m plus n choose r, ways to choose r items from the union of two sets. Then we will find a different means by, for example, k elements, we can pick k elements from the set n elements and pick remaining r minus k elements from the set with m elements. So what we are doing is that we are initially try to define this part, and then you can check this whole section here, that is m choose r minus k and n choose k. For that we need r minus k is nothing but we have to pick k first. So k can be picked from the number of n elements that is in hand. After k is picked, pick the remaining r minus k. Just pick the remaining one, that is r minus k from m. So basically speaking, what happens here is that, as I told you earlier, the basic definition itself is m choose r minus k and n choose r. So once you pick up k, we have r minus k elements remaining. So r minus k elements are chosen from m elements. Initially k elements are chosen from n element. So that's the basic thought. In fact, the actual definition is it's that way. And via product rule you can actually consider this case of product rule, and then finally you have this definition has been fulfilled. Again, the question of bit strings we can consider here. How many bit strings of length 10 contains exactly 4 ones? Does it sound like the one we have seen earlier? Yes, we saw a similar problem in one of our previous lectures. So find the positions of 4 ones. The order of these positions does not matter when we talk about these combinations. So, but just find the positions of this one. So position 2, 3, 5, 7 is same as positions 5, 7, 5, 3, 2. And remember, this is the string length of 10. And among the string length of 10, I want exactly 4 ones. So that is 4. That is CNR. That is C10 4. That is 210 is what we got. So generalized form, you can have CNR possibilities of bit strings with n length containing r ones. Let's see another proof here. Let n and r be the non-negative integers with r less than or equal to n, and we have a n plus 1 choose r plus 1 equals summation j equals r till n, j choose r. So we can see that we have a combinatorial proof by showing both sides to count the bit strings of n plus 1 and r plus 1. So in the previous slides we just see an example. In fact, you can apply a similar approach to see whether you got the same results. Let's see, as a next step you can show that right side counts the same object. So for example, final 1 must occur at the position r plus 1 or r plus 2 or r plus 3 or till n plus 1. And then we assume that it occurs at kth bit. So let's say k lies between r plus 1 and n plus 1. If it does occurs at the kth bit, then there must be r ones in first k minus 1 positions. So that is k minus 1 choose r, such strings of length k minus 1. So that's the part here. K minus 1 choose r equals k choose r equals j choose r. And basically, if you could identify the actual relation, and initially the k is from r plus 1, but here k is from r, and again j is from r. Thus with this we can also say it is similar to the one we have just seen. Show that if p is a prime and k is an integer such that k lies between 1 and p minus 1, then p divides p choose k. So from our discussion we know that p choose k is equal to p factorial by k factorial times p minus k the whole factorial. Just recall, this is the combination formula that we had, right? As p divides the numerator, p factorial only once. So p is prime, it does not have any factors less than p. So we need to show that it does not divide the denominator, otherwise the p factor would cancel out. So we can say k is less than p. It was given that k is less than p in the question, right? Yeah, k lies between 1 and p minus 1. So p cannot divide k. And since k is greater than 1, yeah, that is also given in the problem. We know that p minus k is less than p, and thus p cannot divide. So that's p divides the numerator but not the denominator. Thus p divides p choose k. So given another this problem with the combinatorial proof, we have n positive integers. If we have n positive integers, then we have this form: summation k equals 0 to n k square, n choose k equals n times n plus 1 times 2 power n minus 2. So why don't we try this out? We have a hint here. Show that both sides count the ways to select a subset of a set n elements together with 2 not necessarily distinct elements from the subset. Yeah, that is the condition given here, 2 not necessarily distinct element from the subset. So with this thought you can try to find this proof. Again, show the left side property or counted. Show that the left side properly counts the desired property here. So our given with the left hand side, so we have to choose a subset of k element from the set of n elements. Again, choosing one of k element in the subset twice. Consider each of the possible subset size k. So here the two cases shows that right hand side should be n times n minus 1, 2 power n minus 2 plus n times 2 power n minus 1. So this is a way of proof that you can go step by step. When you pick an element from the subset, pick one element from one subset of n elements. So you have n possibility there. Then you can see n minus 1 elements are left once you choose 1 elements from it. So total of 2 power n minus 1 possibility to pick for the given subset at that point of time. So you can use the different ways. Say for example, if you pick different element from the subset, the first element from the subset n element as n possibility. Again, once you pick the first element, you have n minus 1 elements remaining there. So rest you can use the subset formula and the product rule to define it. So once we do one or the other one, we can use sum rule, the total possibilities of all the two combinations. So today we have seen some general principles that is behind the Pascal's triangle, and again I just want to focus on the Pascal's triangle and its applications. I don't want to go deep down into this other matters that are relating to actual probability based combinations. In fact, there are many books that talks about binomials, functions and other features of this Pascal's theorem, and I don't want to talk about this, or I don't give you problems based on that as well. So this whole section, this last 3 parts of counting, the basic idea is to give you an idea about permutation, combination and general counting principles, for which I also like to give you more notes on these topics that we have just discussed. And don't get confused with other topics, because as discrete mathematics is quite a subject that we deal with different aspects of mathematics, in which now we are in the mathematics part of probability. And in fact we are not going deep down into the probability, we just seen few parts of it, especially with regards to Pascal's triangle and permutation and combination. And next we are going to see something interesting. We are going to deal about graph theory. So that's going to be your next lecture. I'm looking forward to see you in that lecture. Until then, have a nice time and goodbye.